Okay, before we come to the final calculation in this question, we need to refer back to the filtration equation. So this is the box out that I've been talking about for quite a while now, and basically it's a simple concept that we're working on, and the concept is that the total pressure drop over the filter and the filter medium is equal to the two pressures added together, the pressure drop over the cake, the pressure drop over the filter medium. And here is Darcy's law converted into things that are relevant to filtration, and you can find that within chapter 5 how that equation is derived. So we're told that we're operating under constant pressure, so we're starting with this equation. So that is our total pressure. That's the pressure over both the cake and the filter medium, and that's the viscosity of the filtrate. That's the specific resistance we've just calculated. That's the dry cake mass per unit volume, which we calculated a few moments ago. We're going to need to know the area, or we have the dimension of the filter, so we've got that. And then we have the filtrate volume, cumulative filtrate volume, as we'll see in a minute. And then we have this as a differential equation, dV dt. And that's basically what we've got in Darcy's law. And then we have the pressure drop over the filter medium, typically a filter cloth. Here, instead of specific resistance, we have the filter medium resistance. We'll call that capital RM. And then we have the area again, and then dV dt again. So this comes from applying Darcy's law twice over. Once to the pressure drop over the filter cake, and then secondly to the pressure drop over the filter medium. So if you like, that is the pressure drop over the cake, and this is the pressure drop over the filter medium. Let's call that medium. Right, well, we're at constant pressure. We need to do a bit of rearrangement. Constant pressure means that this is not going to change. So we better rearrange this, and we'll rearrange it for time, because time is certainly going to change. So we have mu alpha c, that's a little c, over a squared. That's all going to be constant. Then we have a v term and a dv. So we're separating our variables. Let's bring delta p over to the right hand side, and we need to do that for both the cake and the filter medium. But don't forget, the delta p we're talking about is the total pressure drop. So in our rearrangement of the algebra, we've got total pressure drop in here. Okay, and we have dV just here. So that's separating the variables. Then we're going to integrate from 0 to t, and they're all constants because by definition it's constant pressure. So we have a volume that goes from 0 to v here, and 0 to v here as well. Not too difficult to integrate. That obviously integrates to t. That is all our constants: mu, alpha, c, a squared, delta p. But make that obvious, it's a. That becomes v squared over 2 in the integration, and then we have mu rm over a delta p, and that becomes v. So you now have the parabolic equation, the classic filtration parabolic equation, which we tend to linearize by bringing v over to the left hand side. So classically you'll see in the textbook this is T over V, and you'll see it as all this lot as being a constant. So I'll just call that M for the gradient. Then this is, as we're taking V over here, this is just V. I better put V there, to be honest, rather than the independent variable. And then we have a constant just here of all this lot. So that is our constant. So we tend to linearize this equation and plot time over cumulative filtrate volume. Don't forget we've done that integration against volume, and we get this straight line where this lot is the intercept and this lot, don't forget the 2 is part of the constant bit, is the gradient to that line. So that's how we classically use the laboratory data to get these values. But we're not in that boat here. Here we need to know, we're being asked for the time for a filtration to take place, so we better stick with our equation as written here. But we don't need this part, because we're actually told in the question that the Rm is equal to 0. So the equation we need is just the filter pressure drop over the cake, which is this. I'll bring the 2 to the front, to a squared delta P, and then V, and that is a little c, it's not a big C. Little c is dry cake mass per unit volume of filtrate, not the volume concentration. So that is the equation that we need to use, having integrated the general filtration equation under conditions of constant pressure, so that's a constant, and having neglected the filter medium pressure because we're told the medium resistance is 0. So the question now is simply putting in values into our equation. First thing we need to do is to obtain what the viscosity is, and that was it's water, 10 to the minus 3, and the area is 0.0314. 0.0314. So if we come back down here, so putting the values in, the filtration time is going to be equal to 10 to the minus 3 for the viscosity. The alpha value that we had, which is the alpha value which we had, which is 6.7 times 10 to the 10. 6.7 times 10 to the 10. Let's get rid of that. 6.7 times 10 to the 10. So that's times 6.7 times 10 to the 10. The dry cake mass per unit volume of filtrate, which I think was 116 kilograms per meter cubed. 2 times the area, which was 0.14 meters squared, times by the pressure drop, which we need to have a look at some data again, and this is part 8. We're not given the pressure drop in pascals, we're given it as a height of mercury, so this is a depth times density calculation again. So delta P is in SI units 0.36 meters times by the density 13,600 times by 9.81, So that's simply H rho G, H rho G. Bernoulli's equation, the static component of Bernoulli's equation, really, if you know your fluid mechanics. So we want 0.36 in here, times by 13,600, times by G, 9.81. Bit long-winded. It would have been a lot easier if we'd just been given the pressure drop. And then the volume of filtrate, which is 4,600 centimetres cubed. So I better write that in sort of longhand. I'm going to have to move it down to avoid clashing with me. So let's bring that down a bit. Good. So that's 4,600. 4,600 times 10 to the minus 6, because we're 100 times 100 times 100, because we really want the answer in meters cubed. Finally, that's the time taken then. So because what we have here is viscosity, specific resistance, dry cake mass per unit volume of filtrate, 2 times the area. Then the pressure drop is all this calculation here, and then we also need the volume, which is what we have over here. So there's an awful lot of numbers to punch into a calculator. We'll give it a go. I think I'll do it in 2 bits. I'll do the top and then the bottom separately, because there's a lot of numbers here. So it looks to me like it would be a good idea to do 6.7 times by 116, and then we can work out, oh no, times by, let's make that 4.6. And not quite so many units, tens floating about. So that gives us 3575. So that gives us 3575 times 10 to the, well, that was 10 to the minus 3. That makes it 10 to the plus 7, 10 to the plus 7. Then that's another 3, 10 to the 4, so that's 10 to the 4 in total. That was 10 to the 3 because I'd already because I made that 4.6 rather than 4,600 in the calculation. So quick check, that's minus 3, minus 3, that's 6, minus 6 in total, that's the 10 there. So that's 3575 on top. And we have on the bottom 0.0314 times by 0.0314 times by 2 times by 0.36 times by 13,600. I need all that to bring the numbers back to something easy, times by 9.81. So on the bottom we have 94. So at the bottom we have 94.7. 94.7. So that is therefore 3575 divided by 94.7 equals 37. 37.8 times 10 to the 4. Near enough. 378. 1, 2, 3, which sounds an awful long time. It is an awfully big number, and of course the reason behind that is that we're a V missing, aren't we? Because in our equation here, this should be V squared. So in other words, I need to multiply what I've just calculated by the volume again. So it's 37830 times by 4.6 times by 10 to the minus 3. So in other words, I can ditch those 3 noughts and ditch that as well. And that just gives us 378 times by 4.6. That looks more like it. The answer then is 17. It says here 38 or 1739 in fact. So to 3 significant figures that would be 1740 seconds. But it's not a particularly good calculator. There's lots of potential for rounding, and it looks to me like the actual error, we're good to 2 significant figures, is that one there. The real answer is 1747 seconds. Okay, that's constant pressure filtration, the time taken to filter that 5 litres during constant pressure filtration.